recording. Okay, so chapter 18. As I look at chapter 18, I'm thinking, oh my goodness, we're very close to the end, right? Very close to the end, because as far as we are concerned, I only go to chapter 20. I don't go into organic chemistry at all. Most of the time, I don't even have time to go over that. But if you look at your textbook, it does go into some parts of organic chemistry, some introduction part. Okay, so let me see. We are starting with chapter 18. Chapter 18 takes us to free energy and thermodynamics. So if you had me in 1411, we talked about a subsection of thermodynamics, which was thermochemistry. So in Chem 1411, the prequel to what we're talking about today, we talked about thermochemistry. And thermochemistry is a small section of thermodynamics. So we're picking up where we left from in 1411, and now we're going into the rest of thermodynamics. Now, everything we're doing in 1411, 1412 is still the first level, sort of the introductory level. We're getting a little deeper, but if you want to continue where we live up in 1412, you want to minor in chemistry and take a class called physical chemistry. Then they cover this at a deeper level, including some physics and some calculus. Anyway, we talked about this before when we're dealing with kinetics. We talked about the different types of reactions, and when you're looking at reactions, what your objective is and what your focus is as a scientist. When you're looking at a chemical reaction and your goal is to manipulate it, you want to ask yourself a question. Are you trying to make the reaction go faster? So if you're dealing with kinetics, your goal is to make reaction faster. So if your goal is to speed up the reaction, then you focus on the kinetics section of chemistry, because kinetics section of chemistry teaches you the principles of making the reaction go faster or slower, etc. Okay, and so we covered that already. In this section, we're looking at determining the more stable product. Okay, so our goal here, I actually, this is incorrect. I'm thinking more of organic chemistry. In organic chemistry, when you're looking at thermodynamics, your goal there is to figure out the path that gives you the more stable product. Here, we're just learning about it. So we're not really determining the path. We're just learning that thermodynamics does give you the more stable product. Okay, so in thermodynamics, we're learning that yes, this section here does ultimately give you the more stable product, but we are also talking about spontaneous reactions. So in this section, our focus will be spontaneous reaction. Okay, so what exactly is spontaneity? We're going to get into that, but before we get into that, we're going to be looking at this reaction energy profile. When people are looking at chemical reactions, there are different groups of chemists that examine chemical reactions. When it comes to someone in thermodynamics, they're always asking which path will produce the more stable product, because for a person in thermodynamics, stability is key. Their goal is to get to the more stable product, and the more stable product is the one that has a lower energy. So remember, for them, the goal is stable product. And remember, in chemistry, stable goes with lower energy. So this is where you have a product that has a lower energy. Okay, what about kinetics? For kinetics, the goal is always the faster reaction. Faster reaction. So these are the guys in chemistry who have a desire for speed. The faster the reaction, the better. And sometimes when you're trying to go for a faster reaction, you sacrifice the quality of the product. By the way, the stable product is also the better quality. Okay? This is also better quality. I've actually heard of this discussion and this conflict existing in fashion, where somebody was saying fast fashion is bad for us, and I'm like, wait, why is it bad? I am like team kinetics. Obviously we want our nice clothes and we want it fast. Like, no, it's lower quality. I'm like, we're back to the argument between thermodynamic group and kinetic group, right? So how can we see that in this graph right here? This energy profile diagram tells you what the two groups focus on. The pink or peach color, these are the thermal groups. The thermal group cares about stability, right? So in this energy profile diagram, we judge stability by looking at the level of product, the energy level of the product, energy level of product as compared to the reactant, compared to energy level of reactant. Okay, so for them, when they look at a graph like this is where their mind is. They're judging where is the energy level of the product compared to the reactant. If the energy level of the product is higher, like we're seeing right here, versus the reactant, this reaction is unstable. It's not preferred. Why? For thermal people, for thermodynamic people, this is a group, their desire a more stable product. I've already said that many times, i.e., lower energy than reactant. So now that we know that this is their goal, when they're looking at this, they're not very happy with this graph, right? Our goal here is to understand the mind. We're learning chemistry as we're learning psychology in a way, right? Psychology, sociology, how these groups interact with each other. But where is their mind? What are they thinking? How are they arriving at the conclusion this is not preferred? They desire a more stable product. How do we get that? A more stable product is the one that has lower energy than the reactant. Looking at this graph right here, if the energy is increasing from bottom to top, then you can see the product has a higher energy than the reactant. This is not more stable according to them. Okay, so they look at the initial and final states of the reaction, and they also study spontaneity. So we're going to be looking at both, but in 1412, our focus will be more on spontaneity, even though in the process we will be looking at product and reactant energy. But our ultimate goal is determining what a spontaneous reaction will be. And you will see that theme occur throughout the whole chapter. Is it spontaneous? Is this not spontaneous? How do we know? Justify your answer. Prove it. How do we know? How do we know for sure? Okay, and can we know it? Okay, and then the guys that like speed, that's me right there. Occasionally I go for quality, but I'm always about, yeah, speed. They like the action, they like the energy. This group right here. For this group, their focus is how fast can we get this reaction? Okay, so they focus on this region of the graph. Remember, this region of the graph is where you have that activation energy barrier, right? This is the one which, if it's very high, the reaction has to work so hard to climb up in energy, get all the way up here, and then form a product. So, for people who care about speed of reaction, intermediate state, ultimately the speed of the reaction, they will want this part of the graph to be lower. So let me use a different color so you can see this better. The lower the activation energy barrier, like the black area I drew right now, the faster the reaction, right? So the group right here, which includes me, we like for the reaction to go fast. Sadly, we will sacrifice the quality to get the product and get it quickly. But as a scientist, you want to be prepared for either scenario. You want to know how to manipulate the reaction to go fast. And if the client you're serving wants a better quality, you want the ability to get a better quality product. You become a better scientist when you know how to produce both results. Okay, so don't, even though I'm saying I'm team kinetics, I had to learn both. And in organic chemistry, man, they will ask you these kind of questions. I remember my teacher asking me, design a pathway. I'm like, there we go. Where you get the fastest product. So I had to think back to this graph right here. And your goal has to be, kinetics. Kinetics get the fast product. Design a pathway where you get the more stable product. At that point, I have to shift my mind. Okay, they want me to get a stable product. That means they want me to think like a thermodynamic person, right? So think that way, okay? When you get to organic chemistry, will they explain all that in that way? No, they won't. I mean, I don't know, because that would be a different teacher. My teacher did not explain things that way. I had to make the connection myself. Okay, so we're now thinking like thermodynamic group, and our focus is spontaneity. So we'll start with defining what exactly is spontaneity. We're trying to make sure all of us are on the same page, right? As we define what spontaneity is. We're told thermodynamics predicts whether a process will occur under a given condition. So we're looking at a chemical reaction, and the bottom line question we're trying to ask is, it may be a chemical reaction, it may be a physical transformation, whatever it is. When they discuss the process here, it could be either chemical or physical. Okay? It can be chemical reaction or a physical change like melting, boiling, whatever. The question we're trying to ask is, will it or will it not occur? So, will it occur under given conditions? Okay? When we think about what happened in Texas a few weeks ago, right? When the news said we're going to have a snowstorm, some of us, not mentioning who these us people were like, yeah, I don't know. Well, guess what? Under the conditions they predicted, it did happen. Okay? And it happened spontaneously. So at some point, we will talk about what kind of environmental conditions are required in order for us to have snow. Yes, in chemistry. So processes that will occur under given conditions are called spontaneous. Okay? Not only that, if it is spontaneous, it's also assumed that you don't have to, so you don't need to add energy. So this is from the point of view of the scientist. If you don't need to add energy for the reaction to occur, it is considered to be spontaneous. How do I know that for sure? They say because non-spontaneous reactions, the opposite of spontaneous, these processes here require energy input in order to even start or to go. Okay, so if you, the scientist, have to encourage the reaction to happen by applying energy, that reaction is non-spontaneous. Okay, so sometimes I apply this to human beings. If I have to encourage somebody to do something, they're not really doing it on their own, then in my head I'm like, this is non-spontaneous. The person is non-spontaneous. I gotta go in there, get involved, apply energy, force them, encourage them, whatever. If they're self-starters, they do it themselves, to me they're spontaneous. Okay, spontaneity is determined by the comparing the chemical potential energy of a system before the reaction with the free energy of the system after the reaction. So with this part here, I want to kind of decode the language. In this section, oh my goodness, the language really matters. Okay, so they're saying here, spontaneity is determined by comparing the chemical potential energy of a system before the reaction with the free energy of the system after the reaction. Personally, I hate it when they do this. What they're describing here is a free energy diagram, the one we just talked about, free energy diagram. Okay, they didn't say all that, so you kind of have to read into the question, what scenario does this apply to? If you compare the chemical potential energy of the system before the reaction, so in that diagram we tend to have a y-axis, x-axis. Y-axis shows us energy, right? X-axis shows us the progress of the reaction, progress. We know that we have the reactants on the left, so these are the reactants. The reactants indicate the before the reaction, and then products will be the after. This is our products. So what they're describing here is this graph right here. Okay, so they mean when you have this graph, the free energy diagram, you can determine spontaneity by comparing the chemical potential energy. So sometimes the energy here is called the chemical potential energy. Remember, potential energy is the energy inside an object, the energy that's stored inside the object, right? And so sometimes scientists lazily just call it energy, or they can be more specific and call it potential energy. So the chemical potential energy is the energy inside the chemical. So if you compare the amount before, or the reactants, with the amount after, you can figure out if that reaction or if that change or the transformation is spontaneous. That's what they're saying here. But even in the language, they change the terminology. Chemical potential energy of the system before the reaction with the free energy. See? So I'm going to tell you here. The chemical potential energy is the same thing as the free energy. Okay? Since words are not my strong area, I work extra hard because I know it's not my area of strength. And I tend to overanalyze words. They mean the same thing, but why they in the middle of the same paragraph, I don't know. Do I change that? No, I don't want to change it because I want us to address this, right? They have a habit of changing terminology. So I'm prepared almost bilingual within the same area of science, okay? Chemical potential energy is the same thing as free energy. Now we have discussed that. So when you compare the free energy before and the free energy after, you can tell if the reaction is spontaneous. If you compare the chemical potential energy before and the one after, you can say if the reaction is spontaneous. Okay? So if the system after the reaction, after, we are looking at this one here, right, has less potential energy, yeah, it's less than this one here. Then this isn't before the reaction, yeah, than the before. This is less, right? This is more. The reaction is thermodynamically favorable. Okay, that's what I already said. So what they're saying here is if you compare the after and the before, and the after, aka the product, is lower in energy than the before, this is, according to that group, thermodynamically favored, okay, or preferred, okay? Now let's judge what kind of reaction this is. A reaction in which the products end up with less energy than the reactants, that means they lost energy, right? So we can see here, judgment, lost energy, because when they started off is higher than when they ended. What do we call that? 1411, exothermic. So, bottom line, in so many words, this whole paragraph is telling us here that exothermic reactions are thermodynamically preferred. You see how you can kind of say what you want to say in fewer words? So you want to know when they're saying it in many words, and you want to know when they paraphrase it in fewer words, because the author of the book is different from the PowerPoint, different from the homework, and different from the test bank. I know it's like 4 different groups of people. So you want to be prepared for whatever, right? Okay. And then they tell you why we're here. By the way, spontaneity doesn't tell you information about fast or slow. Okay. We saw before, spontaneity tells us about a reaction occurring and about stability of the product. Okay? Kinetics tells us about speed of reaction. So once again, we're told this. So when I'm taking notes, do you see how I'm paraphrasing? I learned this in high school, the year I got held back. That year. I'm laughing about it now. I wasn't laughing about it then. But I got with a group of students who studied very well. And what they did was take the textbook and paraphrase. Everything they read, they wrote again in their notebook in their own words. And that's how they learn. And so I learned that skill from them. So it helps when you're taking notes, when you listen to a video or something, paraphrase it. It helps you own the material and it helps you remember. Okay, reversibility process. As we're looking at a spontaneous reaction, we're looking at a reversible process versus reversible process. So any spontaneous process is irreversible. Okay, we'll come back to that because there's a net release in energy when it proceeds in that direction. And so it will proceed in only one direction. A reversible process will proceed back and forth between two end conditions. Any reversible process is at equilibrium. This results in no change in free energy. So let's go back and decode this first paragraph. Okay. And I'm going to use the same picture I had before here, the graph. What they're saying is if a reaction is spontaneous, because the reaction is spontaneous, results in a loss of energy, it is unidirectional. So let me try to write this in a different color. Okay? Spontaneous processes are are unidirectional. Okay? So we just said here that in thermodynamics, what is preferred is a reaction where energy is lost in the process, so the products have less energy than the reactant. If you reverse this, you actually end up with the opposite conditions, which are not preferred. Okay, so let me go ahead and add a page right here to make sure that I am being clear in what I'm trying to illustrate here. What is preferred versus what is not preferred. Now, preferred is different from it happens, right? So scenario one, like I drew before, this is preferred. Scenario two, not preferred. Okay, this is different from it doesn't happen. It's just that in scenario two, for scenario two to happen, something else, something extra has to happen to almost force this to happen. Okay, so what is preferred, as we saw before, is exothermic reaction. This is simple. Higher energy reactant, lower energy product. This is the reactant. This is the product. They already said this is preferred. Okay. Then the energy goes up. Okay. As the energy here is going up, this is not preferred. So what is not preferred is this. Okay. So this is reactant and this is product. Okay. So as we're comparing these two, let me zoom out so we can compare. Remember back there in the beginning, we said a spontaneous reaction is a reaction where the reaction occurs naturally without the scientist having to add energy. You can see right here in the first step, energy is released, right? Exothermic. This right here is endothermic reaction. How do I know it's endothermic? When we have our product, it ends up with a higher energy than the reactant. So somehow it gained energy from somewhere, right? Guess what? Energy is gained or absorbed. So somebody has to give the energy to this reaction. So most likely it's the scientist, you. So by the virtue of the definition, this is not preferred because energy has to be added, has to be added, making this not spontaneous. Okay? So if you can understand the conundrum, the issue here, number two is not preferred because it costs the scientist energy or the surrounding energy. Somebody has to pay energy to the reaction, okay, to increase the energy of the products. That's why this is not preferred. So if this is a forward reaction going from left to right, the reverse is not preferred. Reverse is this one here, where this is now the starting point and this is now the ending point. So hopefully you get that part, okay? If you have any questions, please ask me, because once again, this section here, the first half of it is terminology, and it's a little bit complicated if you can't navigate through the words. But then once you get to the math, it gets a little bit, I would say, easier, because it relies more on the math and less on the terminology, okay? If a process is spontaneous in one direction, it must be non-spontaneous in the opposite direction. This is the forward direction right here. This is forward, and this is reverse. Okay, so in the forward direction where energy is released, this reaction is preferred and therefore spontaneous. In the reverse, because energy has to be gained, it's not preferred and therefore is not spontaneous. Okay, using just the picture. Okay, so we're being told here in a reversible reaction, you can't tell if a reaction is spontaneous or not, just because the reversible reaction results in no change in free energy. And we that if a reaction is spontaneous, energy is being released. Okay, so we'll come back to this. I don't want to spend much more time on this part here. In this picture here, they're trying to show you how spontaneity is one way. When you buy a new shining car, just so you know, I recognize it was pointed out to me by my students who were very observant. This is a different car. I'm like, they're trying to make a point, okay? So I recognize it's a different car, right? It's a different car. But the point is, once upon a time, you buy a nice and new car. Look at how shiny it is, right? You step out on the street with this car, people are like, oh my goodness, look at your car. And then after you neglect it a few years, this is what your car looks like. All of a sudden, nobody's talking about it, right? Your family is like, what's up with that car? You're going to get rid of it? You're like, oh, it's a classic, right? So what they're saying here is, naturally, if you just let things go, things deteriorate with time. They deteriorate. They just go bad, right? If you don't intervene, things just go bad. They go ugly. They become old with time. This happens naturally without even anybody trying to force anything, without applying energy. But if you want to restore the car, to go against nature, right? To make it what it once was, you will have to apply energy. You have to apply effort. Imagine seeing this car here, and you love to restore cars. You have to buff it, and then you have to, do stuff. I know you have to buff it. You have to get rid of all that rust, right? You have to put back the wires together, get some new tires, maybe something. That requires effort, that requires energy. Because you have to intervene, it makes that process non-spontaneous. There is no way in nature this car will not become the car it used to be. You would have to apply effort. And by virtue of you applying effort, you have made that process non-spontaneous. Okay? Okay. So more on the spontaneous process. Spontaneous processes occur because they release energy from the system. I know, I've said this so many times, right? So more spontaneous processes proceed from a system of a higher potential energy, much cleaner language, to a system of lower potential energy, like exothermic. I've already explained that before, so I want to re-explain it. Okay. Now I show you why endothermic reactions are actually not spontaneous, right? So before we read this bullet point here, we saw before endothermic reactions are not naturally spontaneous. Why? Because you as a scientist have to add energy. When you're adding energy, It's not spontaneous anymore because you're adding energy. But they're telling you here, like it's like they're rebutting what you said, right? They said, but there are some spontaneous processes that proceed from a system of lower potential energy to a system of higher potential energy. So this is a one person that tells you, I hear you, but I have seen in life some spontaneous processes that should not be spontaneous, but they are spontaneous. They're going from a system of lower energy to a system of higher energy, but they're still spontaneous. So how do you explain that? Spontaneous, but they should not be. These are reactants and these are products. So we saw from before, based on the definition, these should not be spontaneous, right? But there are a few reactions, some reactions that go against the definition, but they still work. So how do we explain that?
There's eventually a point where it reaches to become spontaneous. So um, it's like a lower level into a higher level, and it's reaching whenever that lower level reaches medium, then it's gonna go to spontaneous.
Okay, we will actually talk about that way, way later on. Right. Later on, we will see that there are certain reactions under certain conditions that are not spontaneous. But as the conditions change, the same reaction that wasn't spontaneous, actually, that ties into your lab. Have you been reading your lab? No, that ties into your lab, right? Where at a certain point, a certain temperature, all of a sudden the reaction that wasn't spontaneous begins to be spontaneous. So at some point we will talk about what you're talking about, but we're not there right now. Okay. And yeah, we'll discuss the same concept you brought up, which is different levels, right? And that has to do with the temperature. Why uh certain areas freeze at certain temperatures where other areas don't. Okay. So we're being told apparently there is more to spontaneity than just the energy change. So we're being told here, okay, there are actually two factors that determine whether a reaction is spontaneous or not. Aha, they were withholding information from us. No, this is how they tell the story in the book. They ask you a question, they push you to a corner where you feel like you have to answer the question, and then they give you the answer essentially. There, the enthalpy change. Enthalpy change is what we were comparing here. The enthalpy is the energy inside the system. The delta H, when we're comparing the energy of the product to the vice versa. That was the enthalpy change. We discussed this in 1411. And then there's something called the entropy change. In 1412, this right here is the new concept right here. Okay, this is that secret thing that they didn't tell us before. Entropy is an energy that's measured, but this is the energy due to randomness. So before I define this, let me start in order. Enthalpy change has the symbol delta H, is the difference between the sum of the internal energy and the PV work energy of the reactants and that of the products. I know it's like we were on a roll and they come and use these weird words again. Okay. So all they're saying here is delta H, which is the enthalpy change, is the end minus the beginning. So essentially, it is the product energy minus the reactant energy. And we'll spend more time on this, so we'll get a chance to decode this. We talked about this in 1411, right? We're reviewing it again. Product energy minus the reactant energy. But they talked about this internal energy and PV work. So in 1411, we defined that the energy that any chemical possesses is broken up in two parts. Okay? The internal energy, which is the energy it just possesses, and then the energy that's available to do work. So each of these energies here is broken up into internal energy and then the energy that does work energy. Okay, so the simplest way to remember it, since you guys won't have to do all this detailed stuff, is the overall energy of the product minus the overall energy of the reactant. Okay? Or in other words, is always the end minus the beginning. And this is the enthalpy change. So the other thing I want to mention as I review 1411 is, remember, thermodynamic group of people, they care about the energy. They're the energy people, right? Because they see that energy is cost. Cost is energy. They're really thinking about money, and for them, energy is cost. Cost is energy. So their focus toward all this chapter is different kinds of energy. First one we're seeing is enthalpy, which we saw in 1411. We're seeing again here the energy inside the chemical. All the energies that you have inside the chemical, add them all together. I'm simplifying this, maybe oversimplifying this. Entropy energy, this is the difference. Once again, when they put the delta here, they mean a difference. Difference between the randomness of the reactants and the products. So each chemical has a random energy. Okay. So delta S here is entropy. Once again, we're looking at the product minus the reactant. Once again, we're looking with the change, we're looking at the end minus the beginning. And we're trying to see how random is the product. Okay. I remember, I don't know if this terminology is still used to describe people. When somebody did something, they'll be like, well, that's so random, right? Randomness is usually a word used to describe highly energetic people, unpredictable people, right? So you can say, hey, listen, I proudly hold this label that I am very random. I consider myself to be very random compared to my spouse. So I will be more random, having a higher entropy, right? I have a lot more energy. I move my hands a lot when I talk. You can't see me right now, but I'm moving my hands. And then my husband, by comparison, he's less random, more predictable. Okay. Yeah. So we're going to be comparing randomness in the product versus randomness in the reactant. So to step back, they're saying when you're trying to judge if a reaction is spontaneous, you can't just judge the enthalpy like we've been doing so far. If you're judging using only that measure, you're only looking at half of the story. You got to combine these two. You got to look at the enthalpy change and the randomness. Okay? So, in other words, it's not that simple. So, going back to this question here, how do you explain an endothermic reaction that should not be spontaneous also being spontaneous? Maybe it has an entropy that makes it spontaneous. Okay? I'm kind of getting ahead of myself because the story. You know what's funny? As a student, I didn't like the conceptual part of this chapter. I'm just being honest with y'all. Oh no. Oh no. Oh no. What did I press? Sorry. I pressed something. I shouldn't have pressed that. I pressed my mouse by mistake. Yeah, I didn't like this section very much. I was like, oh, I can't relate to this. And then when I had to teach the class, I was like, wait, I can totally relate to this. Okay. So before we come back and answer that question, because the PowerPoint does take us in a detour, we're now going to be looking at entropy. Okay, we're looking more into this whole randomness measure, randomness, which sounds so random, right? And the second law of thermodynamics. Wait, what was the first law of thermodynamics again? Yeah, the first law of thermodynamics had to do with conserving energy, right? So back to 1411, first law was about conserving energy. Now we're looking at the second law. Okay. The first law was essentially saying, energy is conserved in the universe in any chemical reaction. We're now looking at the second law and how entropy relates to the second law of thermodynamics. Okay, so what is entropy here? Entropy, we're told, is a thermodynamic function. So in this section of thermodynamics, we have things called functions, and functions are measurable quantities. So instead of calling them measurements or quantities, they call them function. Okay? So it's a thermodynamic measurement, but called a function that increases, its value gets bigger as the number of energetically equivalent ways of arranging the components increase. Okay? So once again, as I said, this section is all about decoding the language. So I'm going to be sharing what this means. Okay? So what they're saying here on the particulate level, so I would say that this is more of the particulate view of entropy. Okay, if you ask somebody, a scientist who likes to look at the units, at the details, because remember, particulate is usually that detail, the level of molecules and atoms, that's that view. If you ask somebody who tends to focus on that view, the atoms and molecules, and for this person, everything boils down to atoms and molecules, and you ask this person, please, can you define or can you tell me from your point of view what entropy is? They will give you this answer. It is a measurement, a function, right? In thermodynamics, whose value, whose number gets bigger when you have many energetically equivalent ways of arranging the components. So, what does this mean? Let me give you an example. I'm going to add a page here. Now, my example, this is the best I have, right? And y'all know I'm open to you guys helping me improve my examples. Years ago, a friend of mine and I decided to, I think, yeah, we were turning a significant age. Okay, I won't say what the age was, but it was significant. And we were like, oh my goodness, we're entering our blank years. Let's go ahead and do a photo shoot. It was mostly just me and her. So we set our camera on auto take pictures, right? Now before that, before yeah, selfies and stuff, we're taking pictures. So by myself, I took pictures. This is me, and I took a bunch of pictures. So since I was the only one in the photograph, there were many pictures of me with one hand up, one hand down. There were so many pictures of me. Okay, I say it like that. Okay, so this is me, this is me, and this is me. This is before selfies, right? And so the idea here I'm trying to use to illustrate energetically equivalent ways to of a system. When there's only one person in the picture, there's only so many variations you can have before the picture. I mean, there's so many variations you can have, right? And there is a limited variation you can have because there's only one person in the picture. So I'm going to write here when there is only one person in a picture, are a fixed number of different poses. Is that how we spell poses? This is how we will spell poses, right? Available. So there's only so many poses that one person can pose. Even if it's 1,000 pictures, there's still so many pictures before you start to repeat the same pose with one person in the picture. But then my friend came along and we're like, yay! And me and her were posing for pictures. This is me and this is her right here. And we are posing for pictures, and because there were two of us, let me tell you something, we were able to get more fun pictures because there were more people. Okay, once again, once I get a better analogy, is one of you help me with a better analogy with this? Oh, let's say my hands are down here, then we'll get a different analogy, because the other one was about clothes and I'm like, guys don't care about clothes.
Are you saying that the neutral pose is where both hands go up?
There's really no neutral. This is more about the number. The more the numbers, the more variation you have, the more random. That's what I'm saying. So when my friend came in, we were able to get more pictures that were different than the pictures I was able to get by myself, because there was more than one person, right? We could do more in the pictures. So the bottom line I'm trying to say here, I'm glad you asked that, is the more people in the pictures, the greater variation in the pictures and more poses than individual. So we had individual. We had more fun, but we're not measuring fun here. We're measuring randomness, right? With me and my friend, be more random. So in other words, let's summarize: more people, more random. Okay. Somehow this reminds me of the Six Flags commercial, right? I don't know if you know that. More flags. This reminds me of uh, the particulate level model in entropy, right? More flags, more fun. More people, more random. Less people, less people, less random. Okay, that's just how my brain works, y'all. This is what they're communicating. So when they go back here and say energetically equivalent ways, these are all the valid pictures that count as different poses. Okay, as the number of energetically equivalent ways of arranging the component increases. So in this story here, the components are the people. When you have many different ways of arranging the people to create a new picture, you're increasing the number of energetically equivalent ways in the picture. Okay? So let's say with me alone, I got around 1,000 pictures. I expect with me and my friend and I will have minimum 2,000 pictures with different poses in each picture, right? Because there's more people, right? Of course, there'll definitely be more because we can do more together, right? So more people, more random. Less people, less random. Now apply that to molecules. More molecules, because this is really about molecules, right? More molecules or less molecules in this case, less random. More molecules, more random. Okay, as long as you can combine the molecules differently, you get more chances of randomness. So now that we've understood that, entropy can then be measured. The greater the randomness, the greater the entropy. So greater randomness, greater entropy. Okay, so when you measure the randomness which has the measurement unit called entropy, has a symbol S and the unit of joules per mole. So remember, it is an energy, and you're measuring the energy for the amount of chemicals. So mole is the amount. The unit for energy is joules. Okay? So this is the formula. Now, for the most part in this class, we just talk about the formula theoretically and say, oh, we recognize this exists, right? We don't do much with it at this general chemistry level, freshman level. But if you minor in chemistry and you go to junior level, you will definitely do a lot of calculations with this, where you will try to figure out the random energy in the system by figuring it out how many random connections or arrangements are available. Remember, W is the number of random arrangements. So I'm paraphrasing that, right? The number of random arrangements possible, which they call the number of energetically equivalent systems. Remember, these people view things from the point of view of, so not only do the arrangements have to each be valid when energy is concerned. So they're saying of energetically is each system, each arrangement, which you figure out, even though they give it to you, you figure it out in the lab. And then K is the scientist who discovered this. K is a constant, but the scientist who was able to coin this phrase and show us how to calculate this, his name is Boltzmann. And so he called the constant after himself, joules per Kelvin. Okay? So random systems require less energy than ordered systems. So random systems tend to require less energy to keep them random than ordered systems. So I like there was this thermodynamic joke which I feel like I should tell it. I tell it every semester and my students just look at me like that's not funny. And I'm like, it's funny to me. Okay. So after we've learned about spontaneity and randomness and everything, a 9-year-old boy who understood the concept of randomness. Oh, okay. I see. I will wait till later on to tell the joke. But in the second law, which we're going to be talking about in a little bit, in the second law of thermodynamics, right here, it says that the total entropy change of the universe must be positive for a spontaneous process, or for a process to be spontaneous. A paraphrase of that is saying things in life are naturally going from a region of order to a region of disorder. In life, things are naturally becoming random. So let me paraphrase the second law of thermodynamics. Okay. When left alone, systems will naturally become more random. In other words, increase in entropy. Increase in entropy. Okay? So if you leave something alone, it would just, with time, it would just get bad, 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 like that car, right? The guy wasn't maintaining it. You can tell. I'm assuming it's a guy. It could have been a girl. Whoever was the owner was not maintaining it. So if you leave things alone, they naturally become more random. And in this context here, you can tell the more random is the natural order of things. So now the joke. The 9-year-old boy's room is a mess. And his mom comes in there and says, "Oh my goodness, how can you live like this? Why is your room a mess?" And so I feel like I'm going to, anyway, the boy tells his mom that he is going in order with the second law of thermodynamics and allowing things to naturally get random. And so when she yells at him and says, "Clean the room," she's like, "Why are you trying to force me to go against the second law of thermodynamics?" And so in the world of chemistry, that's like, it's not like super haha funny, but it's like haha, like silly, Anyway, my husband is going, like it's not even funny. That's his opinion. I just think it's not like, as I said, it's not like haha funny, but the point here is any effort you make to go against nature is going against that second law where systems prefer to become more random, more disorganized. Cars want to become bad, like they want to rot, and bodies just want to, change and become, aged. Anyway, so any effort you or something and keep it in the state it is going against the second law of thermodynamics. Okay, joke that was apparently on. That's okay. Examples. You will have entropy in a system. So here we don't have a just dissolving. We have a physical. So looking at, I'm going to write it horizontally, it horizontally versus vertically. We have sodium chloride solid, like this one here. That was added to water. So it started off as a solid. It was added to water, and the solid became dissolved as aqueous. They didn't even ionize this. Let's not worry about that. They're focusing on the energy change, right? So going from a solid to aqueous, we're told this process has an increase in entropy. So this is increased entropy. So even though they wrote it like this, I like to write it like this because in reality, look at the picture. The sodium ion is separate from the chloride ion. So I don't know why these people, I don't know why. Okay. So sodium chloride compound goes from the compound to forming ions. We have an increase in entropy, right? So you want to be, when given an equation like this, be able to judge, is the entropy increasing? Is it remaining the same? Or is it decreasing? I say increasing because they say increasing. But why? This starts off as one. So you can say compound is like one part. When it gets in water, though, because this is a gets in water, the compounds into ions. So for every one compound, we get two ions or two particles. So when particles increase, so does the entropy. Remember when we're talking about the W value, the more people, the more the W value, the more energetically equivalent ways, and therefore the more entropy. In other words, the more to the party, the more fun. So two ions or particles, more random. Okay? Increase entropy. Any questions about this? So when we go from here, where you have all these units combined as one, and then they separate here, you have more random because you have more units in the ion form. Okay? Let me make sure I have the message part open just in case the question is asked and I can refer to it. Okay. And then, oh yeah, what about this one here? Now we're dealing with another physical process, evaporating. When you go from a liquid to a gas, are we going from a more ordered system to a more random system or vice versa? When you're going from a liquid water to gas water or water vapor, of course the liquid molecules are more organized, right? Relatively more organized. They're closer together. Here, these gas molecules, even though we are seeing less in number, they're only showing us a small section. Okay, so we're seeing less in number. I recognize that. But we have an increase in energy because these have higher energy. Okay, if a system goes from lower energy to higher energy. Now, of course, for us to have a gas, the container will have to be bigger to contain the same amount of molecules, but we're not judging the number of molecules. What we're judging here is the energy. So in the first one, we're judging the number, right? So you can say here, we're judging the number of ions, okay? In the second one here, we're judging the energy of molecule. We're not making more ions here, no, but we're going from a lower energy to a higher energy state. Any questions about that? So please realize how we're not really flip-flopping, but how we're switching the category that we're using to judge these molecules. Okay? So it's like the standard is switching because the scenario is different. And then, as I said, I kind of already mentioned this before, but now we're trying to read it in the context of the slide, which is we're now looking at entropy as it relates, finally. They brought it in before, but never really got to it, to the second law of thermodynamics. So we're told, remember the first law of thermodynamics says that the energy cannot be created or destroyed in a chemical reaction. So as we're making chemical reactions, we have to remember we are not making new energy that has not existed before because energy cannot be created. So you can't come from the lab and say, Eureka, I created new energy that never existed before. All we can use is the available energy. And then you can't even argue, I have destroyed energy. All we're doing here is converting it from usable form to non-usable form. Okay. So when people say in the news or politics, we have an energy crisis. What are we going to do for energy? We're running out of energy. If you can't destroy energy, you can't technically get rid of it. But what you can do is change it from a form that's usable to us humans to a form that, even though it's still available, we just can't use the form it's in, right? That's why they have that whole thing about renewable energy, everybody go green, Earth Day, all that movements. That's just trying to convert the non-usable form of energy back to usable forms, right? There are political parties built on this movement. There are stuff, you know, built on that movement is can we take this energy that's now not usable anymore and make it usable. Okay. Okay. But we're told no matter what we do, the total energy we have in the universe cannot change, but it can be transformed from one form to another. So they say either try to keep the usable form where it is so we don't lose it, or if you make the bad form, the unusable form, then try to reverse it. Okay. Now, moving on to the second law of thermodynamics, this says that the total entropy change of the universe is positive. As we're sitting here talking, things around us are just becoming, things around us are getting bad. They're getting from less random to more random because this is just natural. In the universe, things are getting more random, things are getting more spontaneous. The total energy must be positive for this process. So while we're here, I need to go ahead and detour a little bit. Normally do that, I haven't done. Okay. While we're there's certain underlying things they want you to know, right? Besides all the chemistry, they want you to know the criteria required required for a spontaneous process. Okay? So they have been wanting you to know that, and they have been communicating that, but it's not spelled out. So that's, I feel like that's my job, right? To come in and help you to spell it out. What is the criteria required for a spontaneous process? We learned the first one already. Given delta H and delta S values, we can judge a process. Okay? But what is the standard though? What do we prefer? Delta H has to be negative. Delta S has to be positive. So if delta H is negative, that means the reaction has to be exothermic. Delta S is positive, that means has to be more random. Okay, more random meaning higher entropy, right? And so we'll come back to this over and over again in this chapter, and I'll keep reviewing it even in the next chapter, right? So when you look at a spontaneous process and you're trying to ask, or you're looking at a process in your homework and they're asking you, is this process spontaneous? First thing you want to ask yourself, did they give me delta H, delta S values? If the answer is yes, is the sign on delta H negative? If the answer is yes, that's just half of the question that you haven't really answered the question. You only have half the information. Is the sign of delta S positive? If the answer is yes, then you can conclude, based on the above two signs, the process is spontaneous. Okay? The second thing we're seeing has been noted right here. This is the second part, which is, since the second law of thermodynamics says the entropy of the whole universe must be positive for a process to be spontaneous, what they're saying here is if a process is going to happen and you have the delta S value of the universe, you can use that value instead in the place of number one. So if delta S universe value is provided, we can judge the process. This should be the process, okay? How will we judge it? What criteria will we use? According to this law, it has to be positive for the process to be spontaneous. So delta S of the universe has to be positive. And if it's positive, then the process is spontaneous. And so this is how they're explaining the second law of thermodynamics, which is if you're given this number, delta S of the universe, and you look at the sign on it and the sign is positive, then just by looking at that by itself, you can make a judgment. This process is spontaneous. But what exactly is delta S of the universe, and how do you calculate that if it's not given to you directly? They say if you have delta S of the system and you have delta S of the surrounding, you can add these two and you get delta S of the universe. So if delta S of the universe is not given to you directly, but they give delta S of the system and delta S of the surrounding, you can just add those two numbers, get your own delta S of the universe, and then go back here and make a judgment. Is it positive or not? All we want is the sign, not the magnitude, not the number. Okay? So in the process of going over the criteria, I have also talked about the second law of thermodynamics, but I've explained to you in the context of we will use this information to judge reactions. And our goal in judging the reaction is deciding, is it spontaneous? Okay. So here, if we have a reversible process, delta S of the universe is 0. Okay. So since they said delta S of the universe has to be positive, 0 is not positive. 0 is neither positive nor negative. So I can judge here because as a student, I have these ongoing questions behind the scenes. So is a reversible process spontaneous or not? From here, we can say no, it's not, right? Because delta S of the universe is 0, but they said it has to be positive. So, therefore, not spontaneous. Because delta S of the universe that they have for this reaction does not fulfill the criteria, it is not positive. But if you have an irreversible reaction, which we also call spontaneous, its delta S of the universe will be greater than 0, which means positive. Okay, so before I go into this bullet point, which will require me to explain a lot, do you have any questions? I'm doing a quick check. Any questions?
No.
Okay, doing good then. Now we are moving away from the criteria. We will continue to unfold the criteria as we go along, but we're moving away from the criteria and moving on. Okay. In my opinion, this chapter is kind of spontaneous and random, but it's just how they unfolded. That's why I'm here. If the entropy of a system decreases, okay, so it goes from being random to less random. That's what I'm reading that's what I'm hearing as I read this. If the entropy of a system decreases, actually, let me copy this and move to the next page so I can talk about this. Let me scroll down, add a page down here, because decoding that slide alone requires a little bit of effort. As I said, this section here is the words, man. The words are the ones that get you. Okay, so if the entropy of a system decreases, I'm paraphrasing. When a system goes from ordered to random, okay, so this is me paraphrasing what I'm reading, and I'll even give an example because I like to do the most, right? When a system goes from order to random, like a liquid to gas, okay, now continue, comma, then the entropy of the surroundings must increase by a larger amount. So a system, here I use water. Water is going from a liquid to water, okay? Situation, the change in the entropy, the system is decreasing. Decreasing, so it has to go become more, sorry, from gas to liquid. Like a gas let me start from here. Goes from random, because it's decreasing. It's going from random to more order. So it's the opposite of writing, from random to more order. That's consistent with decreasing. So I have to reverse this part too. I was checking my answer and I was like, too liquid. Okay, finally, is my negative, which is consistent with the entropy decreasing. Then the entropy of the must increase amount. The system to liquid, as in the entropy
Your screen turned off.
must. Oh, okay. Thank you. Okay. I have to do it. Share the screen. Good. Can you hear me?
Yes.
What status and settings? Or I'm trying to make it better.
It's probably because your computer's dying.
Don't say that. Don't speak better. I don't have. Oh, it's been around for how long? 10 years. 10 years. 10 years. 10 to 11 years. But it's doing its best. These are hard times. Okay. So I'll just continue. If it dies again, just let me know, okay? I mean, if it goes out, why my computer like that? Why, Jacob? Oh my goodness, where was I?
Yeah, you're still not. Hold on. Let me refresh my thing.
It's showing that it's me. Ah, what can I do? Okay, hold
Yeah,
on.
yeah.
Hold on.
You're
Is it
showing
better?
your screen. You're showing your
Oh,
screen, but you're not showing the what you're writing.
okay, hold on. I'm gonna come back in, okay, and come back in. Any better? Ah,
This is a black screen.
okay, hold on. Let me share content and see if it's. Come on, collaborate. I'm sharing.
There you go.
You see it?
Yes.
Okay. Let me see. Is the recording still going on? Oh, it's still going on. Okay. No, no complaints. Okay. So we are here. When the system goes from random to, that's what it says, it's decreased. The entropy of the surrounding must increase by a larger amount. Okay, surrounding entropy must by large amount. Okay, so I'll come back and explain this statement right here. First of all, if gas is liquid, we have to ask, to go from liquid, are we actually adding heat to the gas to make a liquid, or the other way, right? Real quick, when we go from solid to liquid, because we are melting, we add, to melt ice, you have to add heat. So to go from liquid to solid, this process releases heat. You have this information. This is a quick recap as we're going through terminology. So when you go from liquid to gas, this is happens in. We know to boil anything, we have heat. So when we go from gas to liquid, we know this process will then do the opposite, heat. Trying to, oh no, hold on. I just saw the reload session. If this is not working, I always have Teams as my backup. I saw that it said reload session. Okay, hold on. Let me